Okay, let's unpack this. Have you ever felt like you're just drowning in a sea of information? Especially, when it comes to cutting-edge tech like data engineering, Apache Spark, all these massive data platforms.
Uh-huh.
You want to get the crucial insights, right? Those aha moments without getting totally bogged down by the sheer volume. Well, that's exactly what we're here for today.
Indeed. Our mission in this deep dive is really to distill the most important nuggets from, well, a stack of sources that lay out the landscape of the Databricks data intelligence platform.
Okay.
We'll explore its foundational concepts, how it tackles real-world data challenges, and what it means for everything from business intelligence, really, all the way to the future of AI.
Right.
What's fascinating here is how these really complex systems are actually designed to simplify, unify, and accelerate enterprise data solutions.
So consider this your shortcut to being well-informed about a platform that's, powering tens of millions of production workloads every single day. We'll uncover how it brings order to the chaos of data, helps build intelligent applications,
Yeah.
and makes sense of just the overwhelming amount of information out there. So as we dive in, how can you maybe apply these insights to your own data challenges? Let's jump right into the big picture then. The Databricks Data Intelligence Platform. It's designed as this unified solution, right, to accelerate, simplify, unify enterprise data.
That's the goal, yeah.
And our sources really emphasize its crucial role in the AI era, especially with Gen AI. They actually state,
Right.
the best Gen AI models in the world will not succeed without good data.
That's a powerful quote. And it's true.
It really highlights why a robust data platform is so critical. But, it begs the question, how do you even begin to build that robust foundation?
Well, that's precisely where the Lakehouse architecture comes in. The Databricks Lakehouse basically combines the best aspects of traditional enterprise data warehouses. Things like AC transactions, that's atomicity, consistency, isolation, durability, which ensure your data is always reliable, always correct.
Got it. The reliability part.
Exactly. And it combines that with the flexibility and, frankly, the cost efficiency of data lakes. The core principle here is keeping data in massively scalable cloud object storage.
So it sounds like you're getting the best of both worlds, that flexibility of a data lake with the reliability of a data warehouse. But aren't there inherent trade-offs there? Like, what's the biggest challenge in truly merging those two worlds, and how does Databricks actually pull it off?
That's an excellent point. Yeah, the biggest challenge has always been reconciling that sort of Wild West nature of data lakes with the strict governance and consistency you need from warehouses.
Right.
Databricks overcomes this with two primary components, Delta Lake and Unity Catalog. First, Delta Lake. It's an optimized storage layer built right on top of your existing data lake. It supports those ACID transactions, giving you reliability and integrity, and crucially, schema enforcement. This means only data matching your defined structure actually gets written, preventing that silent beta corruption.
Okay. Schema enforcement, that's key.
It really is. And then there's Unity Catalog. This provides unified, fine-grained governance for all your data and AI assets. Think of it like a central control tower, offering metastore-level permissions so you can manage access down to the column level across your entire data estate. That includes schemas, tables, files, even your machine learning models, all in one place.
That certainly sounds like a powerful duo for managing complex data. So you've got this unified storage, this unified governance. How does the data actually flow through this lakehouse to get from raw to ready to use? I've heard of something called the medallion architecture.
Ah, yes, the medallion architecture.
Yeah.
It's a really popular multi-layered design pattern. It incrementally improves and refines data as it moves through different stages. Typically involves 3 layers. Bronze, which is for your raw, untransformed data, basically just landed.
Right, straight from the source.
Exactly. Then silver, for cleaned and conformed data where you've applied basic transformations, maybe join a few things. And finally, gold. This is your highly refined, aggregated data ready for direct consumption by BI tools or ML models. This structured approach is what ensures that BI and ML can happen on all your data from a single consistent source of truth. Avoids those data silos and discrepancies.
Okay. Bronze, silver, gold. Simple concept, powerful outcome.
Yeah.
So we've built the house, we've organized the rooms. Now what's the power plant that makes everything run? When we talk Databricks, we absolutely have to talk about Apache Spark.
Oh, definitely.
I know it originated at UC Berkeley back in 2009, born out of challenges with iterative machine learning algorithms on Hadoop MapReduce. But what makes it so uniquely powerful for this lakehouse vision?
Well, what's fascinating here is how Spark was designed as a unified engine right from the start. It offers a single unified API for common data analysis tasks.
Right. That includes standard libraries like Spark SQL for structured data,
Yeah.
MLlib for machine learning, structured streaming for real-time processing, and even GraphX for graph analytics. A Spark application itself consists of a driver process. That's what runs your main function and schedules the work. And then executor processes that actually perform the distributed tasks across the cluster.
And it supports multiple programming languages, right? Which I imagine is a huge benefit for teams with different skill sets.
Exactly. Spark's language APIs are incredibly versatile. While Scala is its primary language, it also offers really robust APIs for Python. That's PySpark, super popular R, Java, and of course, SQL. And the key thing is, the structured APIs like DataFrames are designed to offer pretty similar performance characteristics across all these languages.
Okay, so you're not penalized too much for picking Python over Scala, for example, if you stick to those APIs. Generally, no. Underneath it all, Spark operates on core abstractions. DataFrames, which are usually the easiest and most efficient to use. Then there are datasets, which offer type safety, but are JVM only. And underpinning everything are resilient distributed datasets, or RDDs. All Spark code ultimately compiles down to RDDs.
So even if I'm writing DataFrame code, Spark is translating that.
Yes, exactly. While DataFrames are your go-to for ease and efficiency, it's worth knowing that underneath it all, Spark translates your code to RDDs. Think of RDDs as the highly optimized, low-level engine that makes DataFrames incredibly fast, even if you rarely interact with that layer directly yourself.
Got it. And how does Spark handle the parallel processing part, chewing through these massive data sets so quickly?
It does that by breaking data into chunks called partitions. A partition is basically a collection of rows that sits on one physical machine in your cluster. This allows every executor to work on its piece of the data in parallel. And it's important to remember the distinction between lazy transformations, these just build up a logical plan of what needs to happen, and actions, which actually trigger the computation.
Right. Nothing happens until you call an action, like count or collect.
Precisely. Spark builds up this lineage, this plan for the data frame, so it always knows how to recompute any partition by performing all the prior operations on the input data. That's how it gets its fault tolerance.
Okay, that gives us the robust foundation, the powerful engine. But how do you actually build these incredible data highways? That's where data engineering comes in, turning that raw chaos into structured insights.
Exactly. Data engineering is really about taking raw data from all sorts of sources and processing it for downstream uses like analytics, BI, or feeding machine learning models. The process generally involves three main parts. Ingest, which is just bringing data into the system. And this can be tricky, dealing with disparate sources, data sprawl across multiple clouds, maybe even on-premises centers.
Yeah, the messy reality.
The messy reality. Then transform, processing data through those layers we discussed, like bronze, silver, gold. And finally, orchestrate, which is scheduling and monitoring these pipelines, handling failures, making sure real-time data flows are managed efficiently.
This sounds like a lot to manage, especially with real-time data and all those diverse sources. How does Databricks help orchestrate these complex data flows without data engineers, pulling their hair out?
That's where Databricks workflows come in. They act as the orchestrator for your data processing, ML, and analytics pipelines. They're fully managed services.
Okay.
And they have serverless compute options, which is great for efficient task execution because you don't have to manage the underlying infrastructure yourself.
Nice.
And for running non-interactive code like notebooks, scripts, JIR files, use Databricks jobs. These jobs can be triggered in various ways, manually, on a schedule, continuously, or even when new files land in a specific storage location. Lots of flexibility there.
Okay, now, here's where it gets really interesting, at least based on our sources. Delta Live Tables, or DLT. They highlight how DLT radically simplifies building robust data processing pipelines, like significantly cutting down on code and maintenance. It sounds almost too good to be true. What's the actual magic trick here?
It does sound a bit magical, but the magic is that DLT is a declarative framework. Think about all the boilerplate code you'd normally write.
Oh yeah, error handling, retries, schema management.
Exactly. Thousands of lines sometimes, just to handle retries, schema changes, logging failures in your data pipelines. DLT's radical insight is that it abstracts away like 80% of that boilerplate.
Wow.
It lets you focus purely on the data logic. It automatically detects dependencies between your data sets and manages the pipeline's execution flow. And a key feature for ensuring data quality is its expectations.
Expectations. Tell me more.
You can define constraints on your data using expect. If records violate the expectation, you can configure it to fail the pipeline. Or you can use expect or drop, which prevents those invalid records from flowing further downstream.
Ah, so you can enforce quality rules right in the pipeline definition.
Precisely. Like you could have constraint valid current page expect current page title is not a null. On violation drop row, that ensures data integrity by dropping rows where, say, a page title is missing. DLT also supports pipelines running continuously or on a schedule depending on your cost and latency needs.
So it's not just about moving data, it's really about ensuring good data and making it simpler to do that. And it has built-in monitoring, too. That seems like another massive time saver.
Yes, absolutely. DLT offers robust monitoring and observability features out of the box. You get data lineage, update history, data quality reporting, all viewable through the Pipeline Details UI or by querying event logs.
Okay.
It can also ingest data directly from message buses like Kafka. And for more advanced stuff, there's a function called for-each batch. This lets you write the output of a streaming query to pretty much any location, even external REST APIs.
Whoa, okay. Writing to external APIs from a stream.
Yeah, but when you do that, you need to be careful about idempotency.
Idempotency.
Yeah.
Right. Making sure if you run the same operation twice, it doesn't cause problems, like creating duplicate records in the target system.
Exactly. You need logic to prevent reprocessing calls that already succeeded. Or maybe use repartitioning within for-each batch to control how many parallel API calls you're making.
That's a powerful feature for integrating with external systems, but definitely needs careful handling. And speaking of preventing messy data, how does Databricks handle schema changes? Ensuring clean data, especially when raw sources might evolve unexpectedly.
Schema management is vital, yeah. Both Delta Lake and Autoloader, which is often used for ingestion, implement something called schema enforcement.
Okay.
By default, this means only ingested data that matches the target table's schema is actually written. If the input data schema changes later, those changes are ignored by default. This really helps ensure clean, consistent data in your tables.
So it prevents unexpected changes from breaking things downstream.
Right, it prevents that silent corruption. Of course, you can configure it to evolve the schema if needed, but the default is safety first. And you can easily create data frames, load data from files like CSV, register them as catalog tables using Unity Catalog, combine them with join or union, all while the platform helps manage that underlying schema.
Okay, so all this effort in cleaning, orchestrating, ensuring quality,
Yep.
it isn't just for neatness,
Yeah.
right? It's to unlock the data's true power. And for many organizations, that power comes directly from machine learning. Apache Spark's MLlib library seems to be at the heart of this.
Absolutely. MLlib provides the tools for that entire machine learning lifecycle, from data collection and, crucially, feature engineering through model training, tuning, evaluation, and finally, deployment. And it addresses different types of ML problems. For supervised learning, you've got classification, predicting discrete labels like fraud or not fraud, spam or not spam,
Right.
and regression for predicting continuous values like maybe movie viewership numbers or crop yield. Then there's unsupervised learning, where the goal is more about discovering hidden patterns, things like clustering customers using k-means or Gaussian mixture models, or maybe topic modeling on text data with LDA.
Finding structure in the data itself.
Exactly. It also supports recommendation systems, think collaborative filtering with ALS for movie recommendations and graph analytics for analyzing relationships and networks. That's useful for things like fraud detection rings or analyzing social networks using concepts like PageRank or calculating in degrees out degrees.
Feature engineering sounds like such a critical step, getting that raw data ready for these algorithms. What tools does ML provide to transform messy, real-world data into something a model can actually understand?
Transforming raw data into numerical features is, absolutely critical for a model's success.
Yeah.
MLlib offers a bunch of tools here, things like bucketizer for bitting continuous features into discrete categories.
Okay.
Various scalars, min-max scalar, standard scalar, max-ab scalar for normalization, basically getting all your features onto a similar scale so one doesn't dominate the others.
Right. Important for many algorithms.
Very. It also provides one hot encoder for converting categorical variables like red, green, blue into a numerical format models can actually use. For text data, you have tokenizer to break text into words, and then techniques like TF-IDF for weighting terms based on their importance in the documents.
So a whole toolkit for data prep.
A pretty comprehensive toolkit. And what's also compelling is its integration with deep learning pipelines. This allows you to apply popular deep learning models like Inception v3 for image recognition directly to image and tensor data on Spark. So you're bringing the power of deep learning to large-scale distributed systems.
That's huge. Applying deep learning at scale. Okay, this all sounds incredibly powerful, especially for big data. But with such large-scale processing, optimization must be absolutely key, right? How do you tune Spark workloads to run efficiently and avoid those painful slowdowns?
Oh, definitely. Optimization is crucial. It often comes down to effectively managing partitions and shuffles. Remember partitions?
Yeah, the chunks of data.
Right. So repartition will incur a full shuffle of data across the network, which can be expensive, but it redistributes data evenly. Coalesce, on the other hand, merges partitions that are already on the same machine, avoiding that network shuffle, so it's much faster, but doesn't guarantee even distribution.
Okay, so choosing the right one depends on the situation.
Exactly. Both impact parallelism and can optimize jobs significantly. Another big one is caching. Caching tables or data frames using different storage levels like memory-only or memory-on disk can massively speed up iterative computations like in machine learning training loops.
Because you're not reading from the source over and over.
Precisely. You keep that frequently accessed data right there in memory or on local disk for quick access.
Makes sense. And when things inevitably go wrong, which, let's face it, they always do in large complex systems, how do data engineers effectively troubleshoot within Spark? What are the common culprits they should look for?
The Spark UI is your absolute best friend here. It's essential for monitoring job progress and, crucially, identifying where things are going wrong or slowing down. Common errors fall into a couple of buckets. You have analysis errors, which happen before tasks even launch. Usually simple stuff like a misspelled column name or a syntax issue in your code.
Right, easy fixes, usually.
Usually. Then there are execution errors, which happen during runtime. These are often trickier, maybe due to unexpected data format issues, null values where you didn't expect them, things like that.
Got it. What about performance issues, like slow jobs?
Yeah, slow jobs are common. If you see slow tasks in the Spark UI, often called stragglers, that's your immediate red flag.
Stragglers.
It means some tasks are taking way longer than others. This often points to uneven data partitioning, meaning some executors just have way more work to do than others. Sometimes you can mitigate this by enabling speculation where Spark proactively launches copies of slow tasks.
Interesting. What about slow reads or writes?
Slow reads writes can point to bottlenecks like network connectivity issues or problems with data locality, meaning Spark couldn't schedule the task close to where the data actually lives, so it has to fetch it over the network. And finally, the dreaded out-of-memory error. This can happen in the driver process or in the executors. It often occurs if you're using user-defined functions, UDFs, inefficiently, creating way too many objects in memory.
Ah, the UDF trap.
It can be. Using the built-in structured APIs is usually much more memory efficient. Enabling cryo-serialization can also help by storing objects more compactly.
Okay, lots to look out for. But the Spark UI is key. Now, if we connect all this technical stuff back to the bigger picture, it's clear these capabilities aren't just theoretical. There are real-world impacts. Can you give us some concrete, maybe even surprising examples of businesses leveraging this platform to solve major problems?
Absolutely. The impact is really tangible. Take Block, for instance, formerly Square. They proactively identify and prevent fraud using AML. Imagine the scale of transactions and potential fraud attempts they deal with daily.
Massive scale.
Huge. They implemented Delta Live Tables, DLT, to boost their development velocity. It enabled their internal teams to manage these complex fraud detection pipelines and settings much more easily using CI/CD practices. It dramatically sped up their ability to respond to new emerging fraud patterns.
Wow, so DLT directly helped them fight fraud faster.
Exactly. Then there's Trek Bicycle. They moved from dealing with weekly, often stale ERP data to what they described as a nearly up-to-the-minute view of their retail operations.
That's a game changer.
Think about it. They said their old retail analytics solution took 48+ hours to much less. Waiting 2 days for sales data versus getting it in minutes? That completely changes how you manage inventory, run promotions, react to the market.
Yeah, that's a massive improvement. Going from days to minutes for critical business insights is absolutely transformative.
It truly is. Another great example is Coastal Community Bank. They managed to achieve what they estimated was 2 years' worth of work in 9 months.
2 years and 9 months. How?
by leveraging the platform to handle both their traditional batch-driven financial systems and real-time data streams seamlessly. And beyond their internal gains, they also simplified secure data sharing with their partners using Delta sharing, which is built on an open standard.
So efficiency and better collaboration.
Right. And one more, Powys Teaching Health Board over in Wales, they modernized their entire tech stack. They estimated this kind of overhaul would traditionally take maybe 5 to 10 years.
Wow.
But they did it much, much faster with Databricks. This enabled them to actually move towards predictive analytics, enhancing patient care, improving outcomes. They basically feel they've become future-proof in their data capabilities.
These examples really show the breadth of impact, don't they? Across finance, retail, healthcare, very different industries, all finding value. So bringing it all together, what's the ultimate value proposition here for you, the listener? What's the biggest takeaway from all these capabilities for someone looking to truly harness their data?
I think the core idea is that the Databricks Data Intelligence Platform aims to provide an open, unified foundation for all your data and AI governance, and critically, one that's interoperable across different clouds, data formats, and other platforms.
Right, breaking down silos.
Exactly. This unification is designed to tackle those persistent challenges we talked about, disparate data sources everywhere, the complexities of real-time data. It's about enabling organizations to finally extract that value and accelerate innovation. Concepts like Unity Catalog for governance, Delta Lake for reliable storage, structured streaming for real time, they all contribute to building a more future-proof data infrastructure.
Future-proof, meaning it can adapt.
Yeah, adaptable to new technologies like Gen AI as they emerge and just evolving business needs in general. So yeah, this deep dive has really shown how comprehensive the Databricks Data Intelligence Platform is. From those foundational pieces like Spark and Delta Lake, right up to its advanced capabilities in AI, streaming, and that robust governance through Unity Catalog, it's really designed to provide that single source of truth for all your data. It's enabling, hopefully, rapid innovation and much more confident decision-making.
Absolutely. It's crystal clear that getting your data house in order, really understanding its lineage, ensuring its quality, these aren't just like technical feats anymore. They are fundamental business advantages in today's AI-driven world.
Couldn't agree more.
So as you navigate your own data challenges, what part of building this truly unified, intelligent data platform, maybe it's the raw power and efficiency of Spark, maybe it's the control and visibility from Unity Catalog or the simplicity of DLT, what part sparks the most potential for your journey towards better, faster, data-driven insights?